In their central goal to get a handle on the first stars and universes that enlighten the cosmos, cosmologists are still lacking clarity. However, they are moving closer to illumination. One disclosure, during a period that is the awesome, unavoidable end from momentous disclosures by the James Webb Space Telescope, JWST, is the 1 billion-year time machine that just definitively shut its generally paramount year of observations. This is expected to impact the weak infrared shimmer of the universe's earliest glowing objects. The Webb's vision wandered again into the early universe, only a few 100 million years after the Big Bang, allowing it to gain more and better data about baby universes than any other observatory yet gathered. Its haul of astronomical images has exhibited more bounty than most researchers hoped. Recently, candidate frameworks in the early universe are showing up in numbers that go against assumptions, with small bunches considered to be doing this point. This makes scientists go ballistic. As Charlotte Brickley, an astrophysicist at the University of Copenhagen, said, "We really weren't expecting this in the significant length of time following JWST revelations of incredibly early frameworks." Researchers and observers are mixed. Could the pack of strange, enormous, and brilliant early universes be a result of potential defects in the assessment of the telescope's fundamental observations? If true, could they somehow be reconciled by standard cosmological models, or are they the first hints that the universe is more weird and complex than even our boldest hypotheses had ever accepted? Moreover, was the Big Bang Theory off base? Join us today as we dive deep into how the James Webb Space Telescope has transformed our understanding of the universe. Let's get to the feature, understand the challenges, and return to the point when the universe was thought to have been formed after the Big Bang. The infant universe began cooling. Several million years later, the glowing plasma that filled space settled down, and electrons, protons, and neutrons combined into atoms, mainly hydrogen. Things were tranquil and faint for a period of uncertain duration known as the Cosmic Dark Ages. Then something happened. Most of the material that flew apart after the Big Bang is made of something we can't see, called dark matter. It has exerted a strong influence over the universe, especially in the early stages. In the standard picture, cold dark matter, a term that implies invisible or slow-moving particles, was scattered throughout the universe. In specific regions, its density began to increase, and in these areas, it started collapsing into clusters. Visible matter, meaning particles, grouped around these dark matter clusters as they cooled. Eventually, these clusters densified, and the first stars were born. These new sources of radiation reionized the neutral hydrogen that filled the universe during the so-called reionization era. Through gravity, larger and more massive structures formed, constructing a vast network of galaxies. Meanwhile, everything continued to fly apart. The universe is expanding rapidly. Cosmologist Edwin Hubble figured out during the 1920s that the universe is expanding, and in the late 1990s, his namesake, the Hubble Space Telescope, found evidence that this expansion is accelerating. Consider the universe like a piece of raisin bread. It starts as a mix of flour, water, yeast, and raisins. When you combine these ingredients, the yeast starts working, and the dough begins to rise. The raisins inside represent galaxies. As the dough rises, the raisins move further apart from each other. As the dough expands, the rate at which the raisins move apart increases, resisting their gravitational attraction. This speed increment seems to be driven by the mysterious energy of space itself, known as dark energy, represented by the Greek letter lambda. Inserting values for cold dark matter, normal matter, and radiation into the equations of Albert Einstein's general theory of relativity gives you a model of how the universe evolves. This lambda cold dark matter, lambda CDM, model matches almost all observations of the universe. One method of testing this model is by examining incredibly distant galaxies, from back in the initial few 100 million years after the Big Bang, when the universe was simpler and its development easier to analyze against expectations. Astronomers initially tried to see the earliest structures of the universe using the Hubble telescope in 1995. Over 10 days, Hubble captured 342 images of an empty-looking patch of space, revealing a flood of galaxies at various distances and stages, extending back to times much earlier than anyone had anticipated. Hubble would continue to find some incredibly distant galaxies, such as GNZ11 in 2016, which was a faint smudge dated to around 400 million years after the Big Bang. This was incredibly early for a galaxy, but it did not align with the Lambda CDM model, partly because it was small and had only 1% of the usual mass and partly because it stood alone. Astronomers needed a more powerful telescope to determine whether GNZ11 was an anomaly or part of a larger population of puzzling early galaxies, which could help decide whether we are missing a crucial piece of the Lambda CDM equation. That is why the James Webb Space Telescope, JWST, was built and considered essential as the largest, most powerful observatory ever launched from Earth. The JWST was designed to enhance our ability to interpret the universe. Positioned 1.5 million kilometers away from Earth to avoid regular interference and cooled close to absolute zero by its tennis court-sized sun shield, the telescope features a massive segmented mirror and exquisitely sensitive instruments. These were designed to reveal details of the universe's earliest days never before seen, and this promise was fulfilled as the first revelations came in within weeks of JWST's full operation. The JWST has surpassed even the most ambitious expectations, observing galaxies incredibly close to the earliest epochs of cosmic history, probing the atmospheres of exoplanets in unprecedented detail, and providing stunning new views of galaxies within our own solar system. Yet, it's only just beginning to unveil the full scope of its discoveries. Vision steps by and by into the underlying few hundred million years after the Big Bang, allowing it to gather more and better information about baby galaxies than any other facility. Yet, the underlying question isn't anything less than our true understanding of how the structured universe we know arose from early-stage chaos. Webb's early discoveries could change the opening chapters of cosmic history, which concern not just distant epochs and faraway worlds but also our own existence here in the Milky Way. As JWST researcher Mark McCaffrian, a senior advisor for space and exploration at the European Space Agency, said, "You build these machines not to confirm the view but to break it. You just don't know how they will break." A form of the Doppler effect is used to measure the distances of objects. This is comparable to figuring out the location of an ambulance based on its siren. The siren sounds higher in pitch as it approaches, lower as it withdraws. The farther away a galaxy is, the faster it moves away from us, as its light stretches to longer wavelengths and appears redder. The degree of this redshift is expressed as z, where a certain value of z tells you how far an object's light likely traveled to reach us. One of the first papers on JWST data came from Rohan Naidu, the MIT cosmologist, and his colleagues, whose search algorithm flagged a galaxy that appeared mysteriously bright and unreachably far. Naidu named it Glass C13, indicating its apparent distance at a redshift of 13, further away than anything seen before. The galaxy's redshift was later adjusted down to 12.4, and it was renamed Glass C12. Other astronomers working on different sets of JWST observations were reporting redshift values from 11 to 20, including one galaxy called CERS 1749, or CR2Z71, whose light seems to have left 13.7 billion years ago, just 220 million years after the Big Bang, barely a blink after the beginning of cosmic time itself. These putative detections suggested that the standard story known as the Lambda Cold Dark Matter (LCDM) model might be incomplete in some way. Galaxies became gigantic quickly in the early universe. "You don't expect to see massive galaxies," said Chris Lentott, an astrophysicist at the University of Portsmouth in England. Indeed, in a review published in November, researchers examined simulations of galaxies governed by the LCDM model and found that JWST's early bright galaxies were organized by mass in ways heavier than those that formed simultaneously in the simulations. Some astronomers and news outlets claimed that JWST was breaking cosmology, but not everyone was convinced. One issue is that LCDM predictions aren't always clear. While dark matter and dark energy are straightforward, visible matter has complex interactions and behaviors, and no one knows exactly what happened in the first few years after the Big Bang. Those frenzied early times should be approximated in computer simulations. The other issue is that it's hard to tell exactly how far away galaxies really are. In the months following the first papers, the ages of some of the so-called high redshift galaxies were reassessed. Some were downgraded to later periods of cosmic evolution due to updated telescope calibrations. SUR 1749, for example, is found in a region of the sky containing a cluster of galaxies whose light was emitted 12.4 billion years ago. Naidu says it's possible the galaxy is part of this cluster, a nearer interloper that may be filled with dust, making it appear more redshifted than it really is. According to Naidu, SUR 1749 is intriguing. Regardless of how far away it is, it would be another kind of galaxy we hadn't known about, a very low-mass, tiny galaxy that has somehow developed a lot of dust, which is something we generally don't expect for such distant galaxies. For the very distant galaxies, everyone knew that the most definitive distance estimates would require JWST's most powerful capability. JWST not only notices starlight through photometry, measuring brightness, but also through spectroscopy, measuring light's wavelengths. If a photometric observation is like a picture of a face in a crowd, then a spectroscopic observation is like a DNA test that can tell a person's family heritage. Naidu and others who studied large early galaxies measured redshifts using brightness-derived estimates, essentially just looking at faces in the crowd using a great camera. That method is far from airtight. At a January meeting of the American Astronomical Society, cosmologists suggested that perhaps half of the early galaxies seen with photometry alone will turn out to be misestimated. Yet by early December, astronomers announced that they had combined the two methods for 4 galaxies. The JWST Advanced Deep Extragalactic Survey, JADES, team searched for galaxies whose infrared light spectrum suddenly cuts off at a critical frequency, known as the Lyman break. This break occurs because hydrogen floating in the space between galaxies absorbs light. Due to the ongoing expansion of the universe, the ever-increasing raisin bread effect shifts the glow of distant galaxies, causing the frequency at that sudden break to move too. When a galaxy's light appears to drop off at longer wavelengths, it is farther away. JADES identified spectra with redshifts up to 13.2, meaning the galaxy's light was emitted 13.2 billion years ago. As soon as the data was downloaded, JADES scientists began celebrating in a collective frenzy. According to Kevin Hainline, an astronomer at the University of Arizona, it was like, "Oh wow, we did it, we did it, we did it." These spectra are just the beginning of a new worldview in space science, as Robert Kirshner, a JADES astronomer at the University of California's St. Nick Cruz says the discoveries show that the early universe changed quickly in its initial billion years, with the universes advancing multiple times quicker than they do today. It's like how a hummingbird is a little creature, he said, however, its heart beats so quickly that it's carrying on with sort of an unexpected life in comparison to different creatures. The heartbeat of these worlds is going on a considerably more quick time scale than something the size of the Milky Way. But were their hearts beating excessively quick for LCDM to soar out? As astronomers and the public wondered at JWST pictures, scientists began working in the background to determine if the universes glowing in our view in fact depend on LCDM, or if they simply help to get the numbers we ought to plug into its equation. One critical yet inadequately perceived number concerns the masses of the earliest systems. Cosmologists endeavor to determine their masses to tell whether they match LCDM expectations. The mass of a galaxy is derived from its brightness, but Megan Donahue, an astrophysicist at Michigan State University, states that, at best, the connection between mass and brightness is a fair deduction based on assumptions gathered from known stars and well-studied galaxies. One essential assumption is that stars generally form within a certain statistical range of masses, called the initial mass function, IMF. This IMF limit is critical for inferring a galaxy's mass from measurements of its brightness because hot, blue, heavy stars produce more light, while most of a galaxy's mass is typically locked in cool, red, small stars. However, it's possible that the IMF was different in the early universe. If so, JWST early galaxies might not be as heavy as their brightness suggests, they may be bright but light. This possibility causes headaches because altering this fundamental input into the LCDM model could give you almost any answer you want, Lovell says. Some astronomers consider fiddling with the IMF the domain of the devil. If we don't get a handle on the initial mass function, then figuring out galaxies at high redshift is truly a challenge, said Wendy Freeman, astrophysicist at the University of Chicago. Her team is working on observations and simulations that will help pin down the IMF in different environments. Over the course of the fall, many researchers came to believe that changes to the IMF and other variables could be sufficient to square the early galaxies lighting upon JWST instruments with LCDM. I think it's very plausible that we can accommodate these observations within the standard framework, said Rachel Somerville, an astrophysicist at the Flatiron Institute, which, like Quantum Magazine, is supported by the Simons Foundation. She added, ultimately, whatever we learn, it's about how fast dark matter halos can gather gas, how fast we can make the gas cool off and get dense and make stars. Maybe that happens faster in the early universe. Maybe the gas is denser, maybe somehow it's flowing faster. I think we're still learning about those processes. Somerville also studies the possibility that black holes interfered with the baby universe. Astronomers have observed a few shining, very massive black holes at a redshift of 6 or 7, about 1 billion years after the Big Bang. It's hard to imagine how, by that point, stars could have formed, died, and then collapsed into black holes that consumed everything surrounding them and started spewing radiation. However, if there are black holes inside the putative early galaxies, that could explain why the galaxies appeared so bright even if they're not very massive, Somerville said. Confirmation that LCDM can accommodate at least some of JWST's early galaxies appeared a few days ago. On Christmas, astronomers led by Benjamin Keller at the University of Memphis examined a handful of significant supercomputer simulations of LCDM universes and found that the simulations could produce galaxies as massive as the 4 that were spectroscopically studied by the JADES team. These 4 are notably smaller and dimmer than other purported early galaxies, such as Glass C12. In the team's analysis, all of the simulations yielded galaxies the size of the JADES findings at a redshift of 10. One simulation could produce such galaxies at a redshift of 13, equivalent to what JADES observed, and 2 others could build the galaxies at an even higher redshift. None of the JADES galaxies was in tension with the prevailing cosmological model. Keller and colleagues posted the preprint on arcs4.org on December 24. Though they fell short of breaking the prevailing cosmological model. The JADES galaxies have other remarkable characteristics. Their stars seem uncontaminated by metals from recently exploded stars. Rearline says their population 3 stars, the eagerly sought-after first generation of stars to ever ignite, and they might be contributing to the reionization of the universe. If this is true, JWST has now looked back to the mysterious time when the universe was set on its current course. Despite these broad discoveries, scientists remain in a state of flux, continually testing, analyzing, and re-examining the data provided by the James Webb Space Telescope, JWST. The telescope's remarkable capabilities offer a tantalizing glimpse into the earliest moments of cosmic history, but the complexities of interpreting this data highlight the challenges inherent in unraveling the mysteries of the universe. As researchers delve deeper into the observations yielded by JWST, they face a multitude of questions that defy simple answers. The discrepancies between theoretical models and observational evidence spark debates within the scientific community, driving further investigations and refinements of existing theories. Each new discovery serves as a catalyst for advancement, pushing the boundaries of our understanding and opening new avenues of inquiry. As scientists continue to sift through the wealth of data provided by JWST, they do so with a sense of humility and awe for the vastness of the universe. Every observation offers a fleeting glimpse into the cosmic tapestry, inviting us to ponder our place within the grand scheme of existence. While the journey toward enlightenment may be fraught with challenges and uncertainties, it is ultimately a journey worth undertaking, an odyssey that promises to broaden our horizons and deepen our appreciation for the wonders of the universe. In this ongoing quest for knowledge, collaboration and interdisciplinary dialogue play crucial roles. Scientists from diverse fields come together to share insights, challenge assumptions, and collectively push the boundaries of understanding. Through collaborative efforts, researchers can leverage their individual expertise to tackle complex questions and unravel the intricate workings of the universe. Moreover, the significance of JWST extends beyond the realm of pure scientific inquiry. Its discoveries have the potential to inspire future generations, igniting a sense of wonder and curiosity about the universe. By fostering a deeper appreciation for the beauty and complexity of the cosmos, JWST serves as a catalyst for scientific literacy and public engagement. As we navigate the intricacies of astronomical exploration, it is essential to maintain a sense of curiosity, humility, and openness. The universe has always been, and will continue to be, full of surprises, challenging our biases and inviting us to explore new frontiers of knowledge.